So today I'm going to talk about the Large Magellanic Cloud, or the LMC, how it will be host to a sizable number of gravitational wave sources detectable by LISA, and how we can potentially use these signals as a probe of the LMC's structure. As many of you know, gravitational wave astronomy has made fantastic strides over the last few years. The first direct detection of the strain produced by a binary black hole merger occurred just 4 years ago, and since then, gravitational waves have also been detected from a neutron star merger. However, the ground-based laser interferometers used in such cases are unable to detect lower frequency gravitational wave sources, including compact binaries, the coalescence of massive black holes, and stellar tidal disruption events, due to seismic activity and instrument length constraints. Here pictured is the Laser Interferometer Space Antenna, or LISA, which can detect signals with frequencies as low as 0.1 MHz by going to space. Many exciting astrophysical sources include an accelerating quadrupole moment, representative of a system shape, and therefore can emit gravitational radiation. A particularly interesting class of such objects are white dwarf binaries due to their prevalence. In fact, there are so many in the Milky Way that they contribute to a background confusion noise, overwhelming LISA at certain wavelengths. Nevertheless, LISA is predicted to resolve over 10,000 galactic double white dwarfs. Scientists have shown that these can be used to constrain structural features of the Milky Way, like the mass and shape of its disk, bulge, and bar, as seen on the right. Gravitational waves are quite useful in this context, since they are not subject to the same limitations as electromagnetic radiation, like dust extinction. The satellite galaxies of the Milky Way, due to their proximity, may also contain enough LISA detectable binaries for such analysis. The LMC, or the Large Magellanic Cloud, is the Milky Way's largest satellite and one of its closest neighbors, making it a prime target for LISA. Indeed, conservative predictions have estimated the LMC will house over 100 LISA detectable double white dwarfs. The LMC is 50.1 kiloparsecs away and has a well-studied structure. It extends towards Earth with a full width half maximum of 2 kiloparsecs based on the distribution of CFID variable stars, and includes a central bar, a dominant northern spiral arm, and subdominant northern and southern arms. These features are all embedded in a disk, which is inclined by 25 degrees and oriented at a position angle of 150 degrees. LMC stellar mass estimates range estimated from rotation curve modeling mass to light ratios range from 1.5 to 2.7 billion solar masses. The LMC's total mass, which is dominated by dark matter, has been estimated by rotation velocities as well as the interaction between the LMC and neighboring galaxies and stellar streams. It has been found to be as high as 450 billion solar masses, nearly a third of the Milky Way's mass. The exact value is important for understanding the larger system, which, as pictured on the right, includes the neighboring galaxy, the Small Magellanic Cloud, a largely gaseous disk that connects the two galaxies, and a large gaseous streams that extend towards and away from the Milky Way. These features have all been attributed to either strong interaction or collision between the two galaxies, as have the subdominant arms, warping of the disk and bar, the accretion of SMC stars onto the LMC, and recent star formation bursts. Such interaction is highly dependent upon the LMC's mass, as well as its possible future collision with the Milky Way. This leads me to the goals of our project. The basic idea is that we are going to take a mock population of double white dwarf binaries and distribute them across the LMC. Then we'll see how many will be detectable by LISA, and how we can use them to study the LMC. First, we'll need to distribute them in space and time, since when and where The binaries born, based on the LMC star formation history, will determine whether or not it is observable by LISA in the present day. We'll consider three models of distribution, but first, let me introduce our binary population. Our synthetic binary population was generated with the SEBA Stellar and Binary Evolution module. Of course, binaries are not formed as double white dwarf pairs. Instead, they transition through various evolutionary stages, with both becoming white dwarfs after several billion years, 4.6 on average. Since we consider an LMC lifetime of 10 billion years, a lot of binaries don't ever become double white dwarfs. On the right, we see the distribution of periods for binaries once they do become double white dwarfs. This is only their initial periods. Since the energy is lost through gravitational waves, the radius of orbits shrink and their periods decrease over time. The green population with the shortest periods are the only ones that even have a chance of reaching the 0.1 MHz LISA band. Now that we have established this population, let's assign them present-day ages and locations. Our first distribution model is observation-driven, using the LMC regional star formation histories of Harris et al. This was derived from fitting synthetic libraries of color magnitude diagrams corresponding to 16 different ages as a weighted sum to each of 1,376 regions. Their survey includes 20 million stars, but they apply a completeness correction to account for unobserved stars, so that we can take this as a representation of the LMC's 2D mass distribution. And indeed, integration over the total star formation history, we find a total mass of 1.27 billion solar masses, which isn't too off from observation. So we may use the integrated star formation history to distribute the binaries across different regions. We then use the region's individual star formation history to distribute each region's binaries in time. For z-axis, we use a Hernquist potential as a probability distribution. On the bottom left, we see the spatial distribution on the sky, where color represents local binary density. And on the right, we have the same density, but along the line of sight as a function of distance. To better visualize when binaries in each region are born, here we see video representation of the regional star formation histories, starting from 10 billion years ago and jumping over logarithmic time steps until reaching the present day. On the left, we see the LMC in the sky, where color represents local star formation rate. On the right, the total star formation history is added up across the entire LMC. As I hit play, various regions light up with new stars brought to life. We see that there is an initial quiescent period followed by several bursts. The burst approximately 100 megayears ago is thought to correspond to a collision with the SMC. These final time steps are critical in seeding the detectable population, since period shortening through gravitational emission is a slow process. A second model considered in our work assigned binaries the locations and ages of stellar particles, which were the output of a simulation modeling the Larger Magellanic System. As we can see on the sky distribution of binaries on the bottom left, and the line of sight distribution on the bottom right, an advantage of this model is that several of the LMC's discernible features are evident, allowing us to test LISA's ability to finely probe structure, although the simulated stellar particles aren't a perfect match to the LMC structure. A notable disadvantage of this approach is that most of the simulated stellar particles were born 6 billion years ago at the start of the original simulation. Having such an old population means that many potentially observable binaries have merged. In order to provide more realistic age estimates to the binaries model 2, we create a third combined model by distributing binaries in time based on the star formation history of the closest region in Model 1 to the stellar particles in Model 2. On the bottom three graphs, we see the total number of binaries in black and the number of double white dwarf binaries in green as a function of time for Model 1, the observed model, Model 2, from simulated stellar particles, and this new combined model. While Model 3 is reminiscent of Model 1, it is not an exact recreation, since there are different numbers of binaries in each region. While Model 2 appears to have the most double white dwarf binaries at the present day, these binaries are old, and most short period binaries have already merged. Since our work is yet to include dynamical friction, energy loss through gravitational waves is slow to restock the detectable population. So Model 2 actually has the least detectable binaries. After recalculating the periods of binaries based on energy loss through gravitational emission, we consider 5 different masses in the range of observation and see how many are detectable for each model for above a signal-to-noise ratio threshold of 7. Ultimately, we find that models 1 and 3 have between 300 and 600 observable binaries, while Model 2 has about half the number. However, these figures include binaries wherein a white dwarf has overfilled its Roche lobe and is currently engaging in mass transfer. The period of such binaries may increase such that they are no longer observable, and similarly, binaries counted as merged might actually not have. Only 40 to 60% of the total number of detectable binaries are detached and sure Lisa sources. If the total mass of double white dwarf binaries exceeds the Chandrasekhar limit, upon merger, electron degeneracy pressure will not be able to withstand the combined object's self-attraction, likely resulting in a supernova, such as that on the right, which left over this X-ray remnant. Double white dwarfs are difficult to observe, so their role in such events is poorly understood. Assuming equal mass ratios, we find that many such supernova type 1a progenitors will be observable by LISA in the LMC, as has been previously predicted for the Milky Way. The relationship between LMC stellar mass and the total number of LISA detectable binaries is linear. However, the dependence of Model 2 presents a complication. Given a certain number of detections, it's difficult to disentangle if the number is greater due to a high mass or recent star formation activity. This degeneracy is relieved by considering the periods of detectable binaries. For all mass models, we found our older population has a median period approximately 1.2 minutes shorter than for our models with highly active star formation. Thus, the number of detections can be used to estimate stellar mass, with Dr. Valeriya Korol working on error estimates. If one wishes to comment on the total mass, parameterized relations for the dark matter content of satellite galaxies may be applied. Looking forward, we hope to quantify how detectable binaries can be used to constrain the LMC structure. We are aided by the fact that detectable binaries have relatively well-constrained sky location errors, as can be seen in the bottom left. As an example of such an application, on the right we plot the LMC's density profile, going out from the center of the central bar along the major axis. The blue is taken from a Gaussian kernel density estimate using the sky location of about 600 detectable binaries, whereas the black data points are taken from observation of light from orders of magnitude more stars. Future efforts may also address the LMC's contribution to LISA confusion noise, as well as the number of detectable binaries in the entire Magellanic system. In our work, we have distributed a synthetic binary population across the LMC in space and time, using 3 different models and considering a range of stellar masses. We find that several hundred LMC double white dwarf binaries will be detected by LISA, many of which are supernova type 1a progenitors. If you are interested in using our LMC binaries, Just let us know.